Okay, good afternoon. We're going to get started. I'm very excited to introduce our next speaker, Limor Fried, aka Ladyada. Ladyada is an impressive hacker and engineer with an undergrad and master's degree from MIT's Department of Electrical Engineering and Computer Science. She is the founder and owner of the New York City company Adafruit, which she started while still a student, and her company impressively has never taken on debt or external funding. She's an advocate of bringing production back to the United States, and Adafruit is in the top 20 of manufacturing companies in the United States. She's also a strong advocate for lifelong learning. In fact, she described her company as a tutorial or education company with a gift shop at the end. Most importantly, though, all of her tutorials are open source, and she is a leader in the open source community movement. Ladyada has the honor of being the first female engineer who has graced the cover of Wired magazine. She has also earned awards from Fast Company magazine, Entrepreneur magazine, and from the Electronic Frontier Foundation. Most recently, she was recognized as a champion of change this year by the White House. We welcome to our Mad Scientist Conference, Ladyada.
Well, thank you for having me so much. This is awesome. We have this really cool rig that's going to follow me around as I give you a tour of Adafruit. As I was kindly introduced, we are in Manhattan. We're downstate from you guys a little bit, but we're in Soho. So there's like the Prada store, the Apple store, and then like electronic manufacturing, which is, I think, is really cool. Because this is like a dream come true to me to have all this manufacturing ability so I can take the engineering designs in my head and make them real. So yeah, we're here in the factory. This is the factory where we are, and this is my desk. This is where I do my engineering, and I design software and electronics, basically to get kids at heart, anybody excited about engineering and electronics. And I can show off one of the projects that I've been working on. So this is a board called Circuit Playground. And the idea behind this circuit board is it's an open source, $20, everything all in one. You can learn electronics, you can build Halloween costumes, you can do science experiments. It makes like really cool LED lights. We just posted a project today where you make a yo-yo using Circuit Playground, kind of get yo-yo shaped. And as you're doing yo-yo tricks, the sensors and LEDs change their designs and colors. So this is a cool way of showing people who may not necessarily think that they are interested in engineering, how engineering can be about art and design and creativity, not just op-amp equations and Fourier transforms. I love those things, but it's more to it than that. So how about we take a tour of the factory? We're on this cool cart, so you're going to see me move. So now we're heading towards the manufacturing zone. And we do all of our manufacturing and shipping and design here in-house, which gives us the ability to move very fast, learn a lot from the manufacturing process, and be really dynamic. If we were outsourcing all of our manufacturing, it would be weeks or months between an idea and even getting a prototype. Because we do it in-house, we can get an idea prototype done in a couple hours, a couple days. We can get a product out in a couple weeks, which is amazing for most hardware manufacturers. So this is the fab department, and you can see some of the desks where we do rework and design. We use rapid prototyping technologies like 3D printing and a machine called an other mill, which is a CNC mill that can cut out circuit boards. Not good for large-scale production, but excellent for getting that first prototype ready to prove the concept. So here is like a testing jig that we use for testing. This is a cellular module that we test. And this tester jig has this really cool clamp on it. So like when we're ready to test, we put the board in here and it pushes it down. And then we use off-the-shelf electronics like an Arduino and LCDs to do the testing. And then we 3D print pieces to make the tester, like the physical tester. And we also laser cut pieces to hold everything in place. So we're doing really fast turn, fast design, very dynamic. Like I updated this tester yesterday because the previous tester was good, but it had a little bit of a failure rate. I wanted to get that failure rate down. So we redesigned it in a day, something we can do because we do things in-house. Again, if I had an outsourced tester design, it would take weeks, if not months, to get that update done. Okay, so let's go to the exciting stuff over here. So here's the machinery. I love equipment. So these machines are like, they're awesome. Okay, they're robot friends. They help us make things faster. They're extremely precise. And we'll start over at the end. Okay, the cart going. So this is called a line, and it's because it's a line. It's a line of equipment, and one machine's output feeds into another machine's input. It's like human centipede but with electronics. And over here is the board loader and the stenciler. Do you want to go all the way to the board loader? Okay, we're gonna get there. I'm gonna start all the way at the beginning. So when we get circuit board designs, we get them panelized. So this is a panel. So you never make one board at a time. It doesn't make sense. You want to make like 20 or 30 at a time. So what you do is you panelize it. Each one of these is a cellular module. That's that tester I was showing you. And they come in a panel, and then when we're done, you can see these little notches. We break this apart. You just use pliers and you break it apart. What's cool is basically when we feed this into the machine, it makes 20 at a time. Very efficient. So over here is the board loader. So the board loader, it's like a Pez dispenser, but for circuit boards. You put a stack of PCBs in, and it just pops on and feeds one at a time. You can do this by hand, but we have a robot friend, very happy to do this day and night. So that's the board loader. The next machine, after the boards have been loaded in, they go into the stenciler. And the stenciler is really cool. So what happens is that you have that circuit board, and you have to put solder paste onto it, because normally if you're soldering by hand, you do like one pan at a time. Not fast enough. These machines can do thousands at a time. What you have to do is you put a deposit of paste down, and you basically screen print it on, and it's like liquid metal. It's like a peanut butter made out of metal, and it's little metal balls, microscopic balls in like a liquid concentration, and then it's just a little bit sticky. So when you put the paste down on the circuit board, then you put the parts on top, they stick on. So what you do is you get a stencil. This is a stencil, and maybe you can see the holes in the stencil. So this is a 2 foot by 2 foot stencil, and you can see my hair is really pink, so it can come through. And it's very precisely made. We get these made in New Jersey. You need to have a custom machine to make these. We don't make that many stencils. And it squeegees on that solder paste like super precisely. That's what that stenciler does. So after the board goes through the stenciler, and this stenciler does like optical inspection to make sure that the paste is like perfect. It goes to the pick and place. Oh, actually, you know what? I'm going to grab a board to show you a stencil board. I totally just grabbed it. Okay. So see this board? See how it's got that kind of grayish stuff on it? That's solder paste. Okay, so once you have the solder paste on, and it's got that stickiness on it, you're ready to place the parts. So the way parts come is on reels. It comes like this. It's just like a reel of parts, and there's like 3,000 components on a reel. And this is really nice. It's easy to pick them up and move them around. And basically what you do is you put them in a thing called a feeder. And it feeds one part at a time into the pick and place. So you get these parts on the reel. That's not good enough. You have to like feed it in. So these things over here are feeders. I'm not going to take them out because they're loaded, but I'll take out one that's over here. This is a feeder. These look so cool. These are like awesome. I think I can fall out. This is like a special kind of gun. So this is a feeder, and you see here this round area. This is where the reel goes in, and then you just feed the tape through. And this is like a mechanized little advancer. And as you click it, or the machine clicks it, it feeds one part in one at a time. So it's very fast. It's very reliable for the most part. It can feed thousands and thousands of parts extremely fast, one at a time. So it's a feeder. So the big thing is you have to kind of like keep the machines going by constantly changing out the feeders, because you have 2,000 parts and they're always running low. So like the person who runs the pick and place machine has to basically load the feeders in, and the human error that can occur that we don't have because we have a good process is making sure the right feeder goes in the right location. So these are the two pick and places. We have a Samsung 481 and a Samsung 482. Samsung makes phones and tablets and computers and stuff, but they also make the machines that make the machines. So they do a really good job. Like, these are excellent pick and place machines. They're very reliable, they're durable, they're very fast. And what we do is we have one machine that is extremely fast, but it can only place small parts. And that's the 481. And then the 482, it's not as fast because it only has 6 nozzle pickups, but it can do larger parts. So what we do is when we are ready to make a circuit board, we split the job by basically running this program that calculates super awesome math to figure out what is the exact number of parts each place should be placing. And then it tells us, okay, put these feeders on that one and these feeders on that one. And it's like some PhD went crazy figuring out like the perfect knapsack analysis of like what feeder goes in which location and make it as fast as possible. And then after the pick and places are done, they've placed all of the components. They go to a quick inspection station. That's where we have our last chance to take a look at it and make sure like this is correct. The pick and places, they do an excellent job, but it's always good to have one last check before the oven. So we have a book that tells us, here's what we're making, and these really lovely photos to show us what it is that it should look like. And then there's a foot pedal. And so when the board's been inspected, we're like, it looks good to us. We press it and it goes through into the oven. But here's the thing, before here, we can like fix stuff. Once it goes into the oven, it's like it's done. It's toasted. It's literally toasted. It's melting that paste and securing all the components onto the circuit board. It's permanent. Like, you can't really, like, you want to find problems before that happens. This is the permanent step. And so this oven has multiple zones. Each one gets slightly hotter. So it slowly heats it up so there's no thermal shock. From here, it's not too warm until it gets to 277 degrees centigrade. So very hot. And what it does is it slowly brings the temperature up so there's no thermal shock, no like evaporation that happens too fast. And then the solder paste melts all at once. And then the final stages are cool down stages where it takes it from 277 down to like, a little bit more like 80 degrees or so centigrade. So warm enough that you can pick it up with tongs and it's not going to like burn or damage anything. And that happens over here. So we're going to go down. So the oven is like the biggest part because you have to have each zone of the oven heated up, and you have to have enough space so that you have a slow heating up. If you had a very small oven with only 1 or 2 heating zones, it could have a thermal shock, which is where you get failures a lot, like parts pop off or they get burnt because there's inconsistent heating. So this is something you have to think carefully about each step of your line because they have to work together. Issues that come up with the board loader can affect boards later on. And then these are where boards come out. So for example, earlier today, we had this board, and so we had these parts pick and place on, and now the paste is melted, and you can shake it, the parts come off, and we can depanelize it by popping tabs off, and then this turns into 6 individual circuit boards. Okay, and that's not it. So like, that's the surface mount line. So that's called the surface mount pick and place line. There are other processes that you can do. So you can do hand soldering, of course, and we do sometimes have to do hand soldering. But what's more fun is to use a selective soldering machine. And a selective soldering machine is like, it's like a fountain made out of metal, which is really neat. So what it does is inside the body, and it's separate because you have to, it's not an automated process in the same way. You have to load the boards in and be a little bit more careful about it. But what it can do is it has a little nozzle that has like, it just has like it's a fountain. Like metal is coming out of it, liquid. metal at, like, again, 300 degrees centigrade, very hot. Don't put your hand in. And what it does is it will melt that solder, and actually, I'll show it on the board. It's easier. Hey, can I borrow it? Hey, Jelly, can I borrow it?
That one's done.
Okay, thanks. So, like, for some components that cannot be pick and place, like these mechanical connections, what you do is you put them on the board, and then if my finger is the nozzle, it comes up, and it just kind of, like, sprays liquid metal over here, and that causes it to get soldered. So it's a way of processing through-hole components, and basically, you kind of want to minimize through-hole components because it's very time-consuming, and, like, you have to get this other machine involved. So you want to have as many of your parts surface mount as possible, but also have this through-hole process available when there are connections. Like, for example, this is a motor driver for a little robot, and you need to have these strong mechanical connections for where the wheels connect. You can't do it with surface mount, it'll tear off the board. So this is a mechanical as well as electrical design, and this is the machine. And it's kind of like a video game because you have to figure out, like, how to get the nozzle in and going through and soldering all the parts, but you want to make sure that that nozzle spray doesn't, like, go everywhere. So, it's kind of fun. We think a lot about fluid mechanics. All right, thanks, Jelly. Okay, and that's the line. And then there's more parts you can do. You can have hand soldering. Sometimes displays have to be manually inserted or soldered by hand. They can't go through the picking place. There's some components that cannot go through the oven, like displays, microphones, some sensors. They're very temperature sensitive, and so even if they are surface mount or if they're through hole, they can't go through some of these machines because they have to have, like, a more delicate process in place. So that's, where you go through every component. You talk to the sales rep or the apps engineer, and you say, hey, is this reflow friendly, or is this selective solder friendly? What do you think the process should be? And then the board is tested, and we put them, and then we distribute to everybody around the world.
Hello? Yep, we can hear you.
That's it.
Okay. All right. Thank you for the tour. Awesome. So I'll go ahead and ask the first question, and we'll make sure everything's good before we get more complicated questions. Given that you are, like, one of the ultimate hacker makers in the community right now, and then from your factory tour, we can see that it's tough to separate the maker from the tools. In terms of skills and abilities, what do you look for in your employees, and what would you envision as a mobile maker lab of the future?
I think, especially with manufacturing, it's good to have a ability to be flexible, and, like, I don't want to say think like a machine, but these machines, they do what we tell them to do. So we have to be kind of careful about what we tell them to do, because they can, nothing makes mistakes faster than tequila or manufacturing equipment, and you definitely don't want to combine the two. So it's definitely like having a sense of, like, wonder and, like, curiosity, and being willing to work with a machine, and, like, not, it's easy to get frustrated with it. Instead, you should say, like, okay, how can I figure out what is the best way to, like, communicate and get what I need done with this machine? So that's why we have this motto where we say, like, we have robot friends. They're not robot slaves, they're robot friends. So how can we work together to get the projects we want done?
Absolutely. Much better than just considering it a simple tool. Well, thank you. I'll go ahead and open it up to the audience. I'll just repeat the question so we can make sure that Limor hears it. Number one, go ahead.
So one of the things we've been interested in talking about is how do we encourage more innovative thought in the Army? Because it's all well and good we say, oh, we want innovative thinkers, but we need to give them tools to play with. What are we think are the bare minimum tools or resources to help encourage really cool thoughts?
Okay, can you repeat the question?
Yep. So to get innovative thinkers, what are the tools that we need to enable them to play with?
What's really neat about the maker community is they're so fast at identifying what's unique and interesting, because I think the way that you know, electronics, the way innovation used to happen was just like really slow, and it was based on, you know, what would happen years and years out. And what's interesting to see now is, you know, we do a weekly show and tell where we have makers from around the world show up and tell us what they're working on. And it gives us a really interesting insight into the kind of stuff that they're doing, because like they'll come up with new ideas and new projects. So keeping, you know, an eye on the maker community and what they're doing, and seeing what's getting posted to the blogs and what's, you know, what projects people are publishing is my way of maintaining that innovation. Because if you're waiting for what Texas Instruments is going to tell you is innovative, it's like it's too late. Like they're just making chips to make chips. They're not necessarily being creative with them. But I think this is why the maker movement is so powerful. I mean, like, I basically have a huge group of people who are doing like all this like market research and development for me, and then they show up every week and present to me what they think is interesting. And I'm like, you're right, that is really cool. Like the yo-yo project I mentioned before, that wasn't a project that we came up with internally. That was a woman who showed up who is an engineer and said, hey, you know, I really like yo-yos, and I had this circuit playground, and I thought, like, why not make an electronic yo-yo? And I'm like, that's a really good idea. And that was only like 3 weeks ago, and already we're creating tutorials and video content based around that idea that was presented to us.
Fantastic. Okay. Another question? Number 2?
Yes, I have 2 questions. The first one is, what is that awesome thing we're hanging around your neck? And the second one is, what does this assembly line, or what does your line look like in 30 years?
So if you wouldn't mind, Limor, commenting on that thing hanging around your neck, and what does these...
So this is a, sorry, I'll take it so I can show it. Actually, it's clipped. This was a gift. Oh my God, I'm trapped. Okay, so this was a gift. This is the cyber badge, and it was given to me by some kind visitors. And this is a random number generator and clocks. This is really cool. It uses some Adafruit components, and what's neat is that it's a good soldering learning kit. I think the people who designed this learned a lot about electronics, but also it's usable. Like this is actually an example of like how you can use off-the-shelf electronics to make a design that's not only like a cool badge, but functional. So it has like a clock, and it has a number generator, and I think it also can do like a dice project with it. So this is kind of neat. Yeah, it's got the random number generator LED on. And it uses one of the LED backpacks that we manufacture here in the factory.
And the other part of the question, Limor, is can you comment on your assembly line in 30 years?
Wow. I mean, it's going to be really cool. I mean, I can just imagine like drones flying around, like picking up reels and installing feeders. What's interesting is that the overall technology behind pick and place and soldering hasn't really changed that much in 100 years. So I think what we're going to definitely see is, you know, the automation is there, and it's very automated already. I think that what we're going to see is more interesting components. So in the 10 years that I've been doing electronics, when I started, or like a little bit more than 10 years, when I started, a sensor like an accelerometer was $20. And, you know, there was absolutely no way we'd have a pick and place. It was surface mount. It was really hard to solder. It was like very challenging. Now these components that are in cell phones and games are so inexpensive and so ubiquitous that we're going to just see like the ability to make extremely advanced electronic components, products using components that right now I think are impossible, like, you know, double stack BGA and package on package. This is stuff that I can't do now. I think that in 30 years, you know, people are starting to get home laser cutters. It's likely that people are going to have home pick and places.
Something to consider. Wow. Okay, a question from our online audience. I'll go ahead and still repeat it. Number 2.
Right, 3D printed graphene batteries, circuits, PCB boards, drones, will be cool. Will the world of walls be like? What will the world of walls be like in the future? Can you maybe talk about some innovation things you are thinking of into the future?
I'm certainly going to rephrase that question. So given kind of the Internet of Things and all the devices that are present today, what do you see them doing in the near future to distant future?
So the near future to, what was the last word?
With the Internet of Things and how we're getting components into everything, electric components into everything these days, where do you see that going?
Well, we have our own Adafruit IO service, and one of the things that we did was we came up with a bill of rights for it, where we said, okay, if you're using our data logging service, you own the rights to your data. We suggest that, all our examples show SSL encryption because we think that's important. But it's inevitable. I think, in the last year, the advent of $2 Wi-Fi microcontrollers has kind of like flooded the market and shown that pretty much everything that you can imagine is going to be connected to the internet. So it's up to the makers and the people who are designing these to, look at this bill of rights that we published, we worked on with other people, and say, like, how can I make sure that the people that are using my technology, that are using these sensors, have the rights to the data, that they're using it securely, that we're going to care for this data in a responsible manner. But I think it's pretty much inevitable that Internet of Things, it's not new. We've had kind of Internet of Things for quite a while, starting with even something as simple as X10. But those sensors that I said were so low cost because they're in all cell phones and all game consoles and in every device. The idea of like a Fitbit or a $5 fitness tracker would be impossible until now. But nowadays, like, everything's a fitness tracker. I'm surprised this isn't a fitness tracker. It's very easy for us to add sensors to everything. So as engineers, we have to think, like, how are we going to use this sensor data and how are we going to be responsible with it?
Did we get at the question, or is that good, or is there anything else to it? Okay, we'll go to number 2. Next question.
Hi, so I couldn't help but notice the computer on your desk is one of those old IBM Model M's. 30 years from now, what relics do you think we use right now, or excuse me, what technology do you think we use right now is going to be one of those old, antiquated relics like the Model M?
So what pieces of today's technology in 30 years may still have some use, even though they'll be a relic?
I haven't barely been alive 30 years. I think, you see the patterns. We still have telephones, but now they're portable and small and they can do a lot more. Connectivity it seems to be only getting more and more intense. I think, overall, we're still going to use electronics. I have a lot of faith in that, but I think there's going to be a lot more, we take a view that there's going to be a lot more biohacking. People are going to do a lot more biological, like human, environmental integration. I think IoT is the beginning of that. Like right now, IoT is really simple. It's just like, what's the temperature? Is the light on or off? But I think that it's going to become much more intelligent. Like the AI it's not going to be, I think, like Terminator, but it will be more like your computer is going to, and the computers that are inside everything are going to know your patterns. They're going to say, like, okay, I know that every Tuesday you like to have, your coffee at 7 in the morning and you like it with no milk and no sugar, but then on Sundays you like to have tea and a bagel, and it'll automatically learn these patterns and adjust its behavior to match what you're doing. That's kind of like the closest thing, I think. I'm kind of looking at the sensors and technologies. What I'd like to see is, even from 15 years ago, educational electronics has gotten so much better. It used to be extremely challenging to teach people programming and electronics. It was like, okay, get your CPLD and a bunch of 555 timers and good luck. And I think now what I'm seeing is it's becoming more inclusive. It's getting a lot easier because the parts are getting less expensive. It's going from a $500 hobby to a $20 hobby, and that just means that we're going to be able to reach more people with the technology that we're designing.
If I can ask a follow-on question about that. So you've commented a lot on the sensors and being able to bring data in. When you have this collection of data what do you see as the analytical challenges ahead for how we would do what could be a big data problem in a single person?
This is tough because, what's funny, it's like even fitness trackers, I remember reading, like, they don't really work, like they kind of guess and they do a lot of heuristics, but what would be challenging for us is, it's like, I remember that, I think it was like Vannevar Bush, he did like a project with some students and was like, okay, let's see if we can recognize a bird using like computer vision, and like that would, like, the idea of recognizing a bird in computer vision has been like an easy problem for like 25 years, but nobody's done it. Like, it seems easy, but it isn't. And I think that one of our challenges is figuring out what's easy and what isn't, and setting our expectations. But I also know that even if computers aren't going to be very adaptable, because, our machine learning might not be, it's slowly getting there, but it's still, in 10 years, our machine learning hasn't moved as fast as I think we thought it would. Humans are very adaptable. And so if we can, it's more about programming the humans than programming the machine intelligence. If we program our humans for our expectations of what the AI will do, I think that's kind of our way of getting around the issue of how difficult it is to do machine learning, machine vision. Like, we're really just starting at it. And I know we have some like these really awesome TensorFlow demos, but like they're still very demo-y. They're getting there, but they're not. It's going to be slower, and it has been slower than we expected. So I think it's more about human programming than computer programming.
Right. So it sounds like the Internet of Things problem is actually easy. It's the big data problem that you're saying is really going to be truly difficult. If we're looking at the, the step sensor, Fitbit type problem of like recognizing steps, it doesn't actually matter if the Fitbit is measuring your steps, right? Like, even if it has an error rate of 25%, it doesn't matter, because what you're actually doing with a fitness tracker is you're programming the human that this is something that they should measure, that they should track, that this is a metric for them to work on every day, and that's why it gets better. Like, wearing a Fitbit doesn't make you healthier. It's programming yourself to think about, I should take the stairs, I should go for a walk, I should go outside. The dog wants to go out. Yeah, let's go out for 25 minutes instead of just around the corner and back. It's like the programming is not just the fitness tracker, which doesn't really work. It doesn't actually track your steps that well, but all it does is help you program yourself. Does that make sense? Yep, understand. Do we have any other questions? Or, Glenn, can you come up to the front, please? Yeah, go ahead. Well, go ahead.
10 years from now, once Adafruit is very successful, of course it will be, what would it take for Limor to go take 2 years to become in the Army?
Oh, that's
what would be attractive to her to come to spend 2 years with us?
I like that question. So in 10 years, when your company is even more successful than you are now, what would it take for you to take 2 years off to join the Army's cyber force to work for the nation?
This is an excellent question. I'm glad you asked that, because I've thought about it. And this is something that I've discussed with my friend, my partner. And what we decided is what I do here at Adafruit, by doing the free tutorials and by designing hardware, if I took 2 years off, there isn't anybody else who would do that. There are people who are doing it, but there isn't somebody doing the exact same things I'm doing that is designing the educational electronics and giving it away and thinking hard about how we're going to educate the next generation of people, especially people who have not necessarily been targeted by the STEM education that we've had in the past. So what I'm doing now is going to help you in 10 years, because what happens now is I do videos and project tutorials, and I do Maker Faire talks or events, and I do these video casts, and I talk to the Girl Scout group that has a first robot, and I talked to them about how they're designing their robot. And in 10 years, those 24-year-old girls who are, they're now 12 to 14, when they're 22 or 24, they're going to be able to join the Cyber Corps, and they're going to be able to help you guys protect the nation. And that's 10 girls when I only had to do one talk. So I am actually more effective by multiplying my efforts out, by doing open source hardware, and this is the goal of open source hardware, and by publishing and doing weekly videos and doing outreach to the community and showing people how engineering is fun. We're able to create a whole new generation of people that you guys are going to be able to recruit, and are going to come in with the skills and knowledge that are necessary to understand cyber defense and cyber offense, understand electronics engineering, and be able to be dynamic and fast, use rapid prototyping, using the maker community and this large group of people. I mean, this is kind of what DARPA has been doing, right? They've been doing these maker and hacker outreach programs to get a large community to come together and solve problems that maybe one person like me can do. I'm not going to drive around the country and look for 10 red balloons, but what I can do is, help work on a protocol that lets people do that faster and better. So that's kind of like what I viewed. And when I went to the White House a couple weeks ago and I spoke to a lot of policymakers there, and I said, what should I be doing? What do you think is the best thing that Adafruit could do? And they're just like, keep doing what you're doing, because what we're doing here is affecting the world, it's affecting the country, and it's very effective. It's working out really well. I go to events and I meet kids, well, not kids, right? I think their kids are like 18-year-olds all the time. And for me, 10 years is not that long, right? 10 years is like, 10 years here, 10 years there, whatever. I got a couple of pairs of pants. For them, they grew up with Adafruit. They grew up with open source hardware. They grew up with the maker movement. They said, when I was a kid, I got a kit or I got an Arduino, and now I'm going to school for engineering, right? I changed the path of my life because of the exposure I've had to electronics. So I think that's kind of how we view what we do here. It's like a multiplying force. And it's also what is really cool about open source hardware. It's like I put up a file or I put up a tutorial and I don't do workshops. Instead, I publish. And when I publish, we get thousands of views on YouTube, and we get tens of thousands of people following the tutorials. And sometimes they buy parts from us and sometimes they don't. It doesn't matter. So I think that's my answer.
Well, Limor, thank you very much. You're certainly leaving your mark on the world. Natalie, do you have another question, or are you coming on up here? Come on, oh, right there? Okay, well, I'll just...
Right here. So, Limor, thank you so much for joining us. We really appreciate it.
Where are you going now?
We're going to flip it around. We're going to make this work. We're totally going to make this work.
Okay.
Technology at its
Okay.
awesomeness.
Oh, wait, things are moving.
Yes.
Hi.
Woohoo! Hey.
Hi, guys.
So we are so excited that you could join us today and talk to us a little bit. And so we officially want to proclaim you a mad scientist. So we have an official proclamation. Woohoo! So that from now and forevermore, yes, you are officially a mad scientist.
Awesome.
And we also have a very awesome coffee mug for you that when you put hot liquid in it, it totally changes colors.
Oh, sorry, I love those. Yeah.
We're going to send these off to you, and we just want to say thank you so much for spending the afternoon with us.
Okay, thank you for having me. It's always been a pleasure and a joy. This is now my second time doing a talk at West Point. I hope to do many, many more. You guys are always awesome hosts.
Thank you so much.
Thank you, everybody.
Bye.